This video is on solving supply and demand problems with equations. We know how to do it with schedules and graphs. Now let's do it with equations. This video assumes that you can derive an equation from a schedule. Now I show you how to do this in a YouTube video entitled Schedules, Graphs, and Equations. Now this link is in the description box down below. Make sure you understand how to derive an equation from a schedule before you watch this video. Here's a typical demand schedule. This particular one, as you can see, happens to be linear, just for purposes of simplicity, and like all demand relationships, it is inverse. Here is the demand curve that shows this relationship on a graph. We call it a curve even though the function is linear because it's just easier to say than function. As you can see, when the price is 4, quantity demanded will be 70. And when the price is 7, quantity demanded is 40. All of these other price-quantity pairs appear on this curve as well, as do all of the ones in between. So here is the equation for this straight line demand curve. Quantity demanded is equal to 110 minus 10p. Again, this is fully explained in the lecture entitled Schedules, Graphs, and Equations, the YouTube link to which is in the description box below. Make sure you understand how this equation was derived from the schedule. So here is the supply schedule. Just like our demand schedule, this relationship is linear, and like all supply relationships, it is direct. And there's the supply curve. And there's the supply curve. And here's the equation. Quantity supplied is equal to 0 plus 12p. Now when the alpha coefficient is 0, we can just omit it. We could just say quantity supplied is equal to 12p. And here we have both the schedules, the curves, and the equations. Now we have to find the equilibrium price for this good or service, given the current market conditions, and the equilibrium quantity exchanged. That is, the quantity of whatever it is that's being sold here that will be bought and sold at that price. It's easy to find the equilibrium price and quantity exchanged by looking at the graph. We know that the equilibrium price is that which will equate quantity demanded and quantity supplied. So equilibrium occurs where the two curves intersect. Here, even though there are no actual values on the graph, we can look at the schedules to see what price equates quantity demanded and quantity supplied. At a price of 5, as you can see, 60 units will be made available for sale by business firms and 60 will be purchased by consumers. Everybody's happy, nobody's going to rock the boat. Were the price 4, consumers would want to purchase 70 units, but firms would only supply 48. Frustrated consumers wanting to get to the front of the line are going to bid the price of this good higher. This shortage, therefore, would cause prices to rise. Were the price 6, businesses would make 72 units available, but consumers would only purchase 50 of them. This surplus of unsold inventory piling up in the producer's warehouse would cause that price to come down. Looking at both the schedules and the graph, you can see that the equilibrium price will occur at the point at which quantity supplied is equal to quantity demanded. Now, let's derive equilibrium price and equilibrium quantity exchanged using equations. Now, let's derive, because, as the supply equation tells us, quantity supplied is equal to 0 plus 12p, let's substitute that for Q sub S. And as the demand equation tells us, Q sub D is equal to 110 minus 10p, let's just substitute that for q sub d. So now we have 0 plus 12p is equal to 110 minus 10p. So let's just solve for p. After we gather our terms, we can see that 22p is equal to 110, and therefore p will equal $5. But what will the equilibrium quantity exchanged be? And therefore p. We can see by the schedules that the equilibrium quantity would be 60 units. But let's do it with equations. What we need to do is to take that equilibrium price, in this case $5, and plug it into the demand equation to find the equilibrium quantity demanded, and the supply equation in order to find the equilibrium quantity supplied. Now, both of those, of course, should be the same if the equilibrium price is correct. And indeed, 110 minus 10 times 5 is 60. And indeed, or if we plug the equilibrium price of 5 into our supply equation, we get 0 plus 12 times 5, 60. 60. So that's about it. It's not all that difficult. And with a little practice, you can get really good at this really quickly. But you'll definitely want to get good at expressing relationships with equations. As a freshman or a sophomore, you'll mostly be working with bivariate relationships, one that can be expressed very easily by schedules and graphs. However, as you progress in your college career, the models you'll be working with will become more realistic. And that means that they will become more complex multivariate relationships, more and more independent variables, all affecting one dependent variable. And as you know, the more independent variables you add to a relationship, the less capable they are of being expressed with schedules and graphs. And it doesn't take much. Schedules become really complicated and difficult to work with and difficult to figure out when there are just two independent variables working on one dependent variable. And it's impossible to show a multivariate relationship with more than two independent variables with a graph. Humans can only envision three physical dimensions. And since each axis requires a physical dimension, height, length, and depth, you're confined on a graph to three variables, two independent variables and one dependent variable. And that's why you'll need to be able to work with equations. You should now be able to easily find the equilibrium price and equilibrium quantity exchanged in a market when you are given a little bit of information about the supply relationship and the demand relationship. But before we move on to the next topic, which would be barriers to equilibrium, let's consider some real world-like variations on this supply and demand analysis theme. Let's examine a little more closely the supply relationship. Notice on the schedule I've added a new row, one where the price is 0. And it makes perfectly logical sense that if the price is 0, no units will be supplied. Now keep in mind, after having watched the video Schedules, Graphs, and Equations, that the value of the dependent variable when the independent variable is 0 is the function's alpha coefficient. And of course, the alpha coefficient is the point at which the function intersects the axis of the dependent variable. And because the dependent variable quantity supplied is 0 when the independent variable price is 0, the supply function will intersect the quantity axis at 0, which is, of course, the origin of the graph. But there's no rule that says the supply curve must intersect the q-axis at the origin, which is where the two axes intersect. Okay, let's consider this possibility. You'll notice that the supply schedule has changed. So let's figure out what the supply curve will look like. First, let's compute the beta coefficient. Beta tells us what the dependent variable will do when the independent variable goes up by 1. And in this case, every time price goes up by 1, quantity supplied goes up by 12. And this remains constant throughout the entire relationship. It's this constant beta coefficient that makes the function linear. So the supply curve is going to look exactly like we have it drawn here, as a straight upward sloping line. But what's the alpha coefficient? Where's that supply curve going to intersect the axes of the dependent variable? It won't be at the origin, that's for sure. So let's see. If the beta coefficient is 12, and we assume the relationship remains linear all the way to where p is equal to 0, the function will intersect the q-axis at 12. That is, when p falls from 1 to 0, quantity supplied falls by 12, from 24 to 12. And would 12 widgets or whatever good or service we're talking about really be supplied if their price were 0? Obviously not, but we need a number there that would keep the relationship linear so we could get an alpha coefficient. So the supply curve would look like this. It would intersect the axis of the dependent variable at 12. What kind of scenario would produce this situation? Well, it could be that there are a whole bunch of entrepreneurs twiddling their thumbs, sitting on their hands, waiting in the wings, waiting for the production of widgets to become profitable. Well, you may remember from high school algebra that the alpha coefficient, or if you use the equation y equal mx plus b, the b coefficient, was where the function intersected the vertical axis. That's because typically the dependent variable is measured along the vertical axis and the independent variable along the horizontal axis. But when graphing supply and demand curves, traditionally, we put the dependent variable q on the horizontal axis and the independent variable p on the vertical axis. Now, how this tradition got started is a mystery to me, but that's the way it's done in every Econ Principles textbook I've ever seen. So this is the way we'll do it here. Therefore, when doing supply and demand analysis, because the axes are flipped, the alpha coefficient represents the point at which the function, whether it be the supply curve or the demand curve, intersects the horizontal axis. But irrespective of the axes, the alpha coefficient will always represent the point at which the function intersects the axis of the dependent variable. Therefore, here's another interesting possibility. Take a look at the supply schedule, and you'll see that it has changed again. As you can see, in this case, no widgets are made available for sale until the price that consumers are willing to pay reaches $3. This supply curve, where it intersects the price axis at a point greater than 0, is far more likely than the other two. In this case, there are no units made available for sale at $2 or below, because obviously the cost of production would be somewhere between $2 and $3 per unit. So at a price below 2, the production of this good or service is unprofitable. So actually there's no supply curve below a price of 3. But above a price of 3, there is a linear supply curve. We know it's linear because the beta coefficient remains 12 throughout the entire curve that actually exists. And here it is. We know the supply curve intersects the vertical axis at a price of 2 because the supply curve would actually look like this. The curve isn't linear all the way to the point where p is equal to 0. Once the price falls to 2, 0 units are supplied. But we need an alpha coefficient. So where does the function intersect the q-axis? To get the alpha coefficient, of course, we need to pretend that the relationship remains linear throughout the entire schedule, all the way to the point where p is equal to 0. So obviously the function will have to extend into the second quadrant of the graph. That's where the values on the vertical axis are positive, but the values on the horizontal axis are negative. And you can see on the schedule that when p falls from 2 to 1, quantity supplied must fall from 0 to minus 12 in order to keep the relationship linear. And when price falls from 1 to 0, quantity supplied must fall by another 12 units from minus 12 to minus 24. So you can see how the alpha coefficient of negative 24 is derived. This is the point where the supply function intersects the axis of the dependent variable q, despite the fact that it's in the second quadrant of the graph. What does it mean that at a price of 0, quantity supplied will be minus 24? What's the meaning of a negative quantity supplied? In real life, it has no meaning. This is just a mathematical construct we must create so we can solve supply and demand problems with equations. You can see, but talking about mathematical constructs, let's go back for just a second and revisit the demand relationship we discussed a few minutes ago. The equation Q sub D equals 110 minus 10P indicates that the demand curve is going to intersect the Q-axis at 110. When the price is 0, therefore, according to this equation, the quantity that will be demanded is 110 units. Although that's a little easier to envision than a negative quantity supplied, it's still just as unrealistic. If the price of something were actually 0, what would be the quantity demanded? Well, it wouldn't be too wrong to say infinite. Obviously, there wouldn't be an infinite quantity supplied, but the few that might be available would be snapped up immediately. The first guy in line would walk off with all of them. Demand curve. So the quantity of widgets demanded when the price is 0 would be far more than this equation would indicate. So suppose you had just gotten your order at a McDonald's, and before you sat down, you stopped by the Fixins bar to get your napkins. Usually you're going to encounter a napkin dispenser something like this. Although it's impractical for them to charge for napkins, the idea here is to impose a cost so the customer won't take more napkins than he needs. McDonald's wants to keep its expenses down, so they don't want customers squandering or wasting the napkins. Fortunately for them, they understand the basic law of demand. The higher the price, the lower the quantity demanded. So in this case, the bigger the hassle in getting the napkins out of the dispenser, the fewer napkins the customer will take. But have you ever encountered a situation where the napkins person was either in a hurry or got lazy and just left them out like this? You can believe that many, many more napkins would be taken. How many would you take? If I saw a stack like this, I'd probably walk off with every one of them. I'd resupply my glove box and my console in my car with napkins. I'd use them to wipe off my windshield, check my oil. Heck, I might even restock my napkin dispenser on my kitchen table. It's not even a napkin dispenser, it's more like a napkin holder. I don't need to impose a cost on anybody. The relationship between the cost of getting those napkins out of the dispenser and the number of napkins taken might very well be linear. But I can assure you that even if it were, the quantity demanded could not be computed with that linear equation if those napkins were just stacked up. The quantity of napkins taken would not be 110 when the price was 0, as in our previous example. That I can promise you. So, at a price of 0, that linear relationship breaks down. So let's wind up this video with a couple of practice problems. Again, it might not be a bad idea to revisit the video entitled Schedules, Graphs, and equations. That link is found in the description box below. Here we have a demand schedule and a supply schedule, and we want to find the equilibrium price and equilibrium quantity using equations. So we'll start with the demand equation. Notice I just made room on the demand schedule for a price of 0. As unrealistic as it may be, let's suppose the relationship remains linear even when the price is 0. We're just doing that to get an alpha coefficient. And here's the equation for the demand relationship. That looks pretty familiar, doesn't it? And now the supply equation. Nothing difficult or unusual here. Everything's very straightforward. Nothing difficult. Now let's set Q sub S equal to Q sub D and replace each term with what's on the right-hand side of their respective equations. I think you'll find it easier if you put the quantity supplied expression on the left. There will be fewer negative signs to deal with that way. Now let's set solving for P. We see that P is equal to 5.5. You might want to pause the video here and calculate that for yourself. Solving for P. Now let's plug that equilibrium price of 5.5 into either the supply equation or the demand equation to find the equilibrium quantity exchanged. Now, but just for demonstration purposes, I'll plug it into both. Solving for equilibrium quantity demanded, solving for equilibrium and equilibrium quantity supplied, and equilibrium quantity. By necessity, they are equal, as long as you've gotten the equilibrium price right. Now these values don't show up on this particular schedule, but if we were to flesh out that schedule more completely, they'd be there. By necessity, they are equal, as long as you've gotten the equal. This next one's just a little bit harder because the supply equation has a negative alpha coefficient. Pause the video here and see if you can work this one out. If you can, you'll know enough to ace any supply and demand problem that you'll need to solve by equation in this class. This next one's just a little bit harder. How'd you do? If you have any questions or comments, be sure to post them on the discussion board. How'd you do? If you have any questions or comments, be sure to post them